if you twist it out.
No, because it twists out, but it's in a little like cannula.
Oh, there's only. Wait, it's in a little what? Cannula? That's a word?
It's like a thing that gets it's like a little tube to put a thing in.
I'm very
I don't know.
impressed. I don't know if I've ever been more impressed with someone knowing the word.
Thanks.
That's like knowing the, yep, the Phoenician verb that taught me that.
Like no new class, I guess.
What are we doing or something?
I don't know. I was just gonna get in the car and see if it was I know Bill had a plan. So now I think we're just gonna go down and see if we're going
I made the mistake of going this summer. And even before, well, like going to the actual part where you can drive, to, like, and not going to the other, the 90% of land that isn't drivable.
Yes.
We got stuck in traffic for a solid 3 hours. It was horrible.
Yeah, then it takes 8 hours to get back, maybe more.
No, because we ended up being like, okay, screw it. It took us, we literally sat in traffic, trying, like, in the park. And we were like, screw it, we can, like, just optimize over this. So if we wait past sundown, everyone's going to leave. And so we can go hiking after the sun sets.
No.
And drive, oh yeah, and drive back at like 10 or 11 and then get back at like 1 or 2. That's the best way to.
Well, 10, 11, 12, 1 now. Get back at 2:30.
No, we got back, it's like a 3.5 hour drive from the because it was really, well, no, the weird thing was, I believe, if I'm correct, the entire source of traffic was just the sidewalk, the crosswalk. To go to your one crosswalk, 2 hours of traffic. To go to your 70 falls. Because there's no traffic light, it's just one person just kind of letting cars through it every minute or two, and it does way too much faster than that. But yeah, never making that mistake.
Don't actually go to the park, go around.
Yeah. My friend Kim boards up there. I asked him, he said, I'm like, I'm never making this mistake.
There's also hot springs up there.
There's hot springs everywhere. Hot springs. I was in Joshua Tree this summer.
Oh, I used to go.
Joshua Tree's like, oh, I have so many photos of going. Oh, it is. My friend has an actual nice camera. I must not, like, half the reason I'm not half the reason I wouldn't. But like, I'm a huge YouTube fan.
YouTube?
Yeah.
Well, how old are you?
21. I mean, freaking YouTube just put out another, I guess it's not that year. They put out a new album a year and a half ago. The premium thing, they've been another 40 years at this point.
Oh, older people then.
So that's one of the bands my dad listened to. I heard it a lot. I love it. But yeah, so I actually got vinyl record player.
Oh.
And so I had to get the Joshua Tree vinyl record. Awesome.
Yeah, my dad was a doctor.
It
Yeah,
is
that's just grasping too.
absurdly beautiful. First 5 minutes. Say hi to S1 for me. Skyward.
All right, let's get started. So today we're going to have part 2 of the exploration lecture, and I'm going to conclude the discussion of exploration methods from Monday, and then I'll also, in the second half of today's lecture, discuss a little bit some of the connections between imitation learning and RL, and that is also something that can be used to address some exploration challenges and also develop some interesting new algorithms. Okay, So quick logistical notes. Homework 4 is due today, so please do make sure that you're getting that done. And then homework 5 will come out probably either tonight or tomorrow. So let's recap the basic motivation behind the exploration stuff that we discussed on Monday. So on Monday we saw that this kind of Atari game, this is called Breakout, is fairly straightforward, but this other game is very, very difficult. And it may not be apparent why that's the case from just looking at the images, but from the discussion on Monday, essentially the rewards in this game don't necessarily tell you precisely what are the things that you need to be doing to win the game overall. So you get somewhat arbitrary rewards for things like picking up the key or opening the door. The game is won by actually traversing through a large series of rooms. And in a sense, what this challenge boils down to is that you need to do a series of events, each of which may or may not be independently rewarding, but you only receive the large reward for winning the game after having done all of the things. Which means that if you're just randomly acting in the world, you're very unlikely to actually see that big reward at the end. So we talked about how there are, broadly speaking, 3 classes of exploration methods, and we saw each of these 3 classes in simple bandit problems, and then today we're going to talk about them in the context of deep RL problems. So we talked about optimistic exploration, which basically amounts to saying that when you see something new, that's good. And this requires estimating state visitation frequencies or novelty. And at the end of Monday's lecture, we saw how we could use a variety of different estimators to estimate whether a given state is novel or not, ranging from explicit density estimation to implicit density estimators using discriminators to something as simple as just regressing onto a random function and looking at the errors of that regression. So typically, when you do optimistic exploration, you use one of these density estimators to calculate an exploration bonus, and then you add that exploration bonus to your reward to get your RL algorithm to actually explore for you. Now, in the context of bandits, we also discussed these Thompson sampling or posterior sampling style algorithms, which, in the case of bandits, learn a distribution over bandit models. In the case of deep RL, these things will learn distributions over things like Q functions, and we'll see that shortly. So the basic idea behind Thompson sampling or posterior sampling is that you have some distribution over either your Q function or a model of the MDP or something of that sort. You sample from that distribution, pretend as though that sample was the right one, and then act according to that for an entire episode. And then we also talked about information gain style algorithms in the context of bandits. So these are algorithms that do some variant of Bayesian experiment design. So they reason about information gain. In the case of bandits, they reason about the gain of information over something like the bandit model from taking different actions and observing different rewards. In the case of deep RL, we'll reason about information gain from visiting different states. Okay, so we finished up our discussion of optimistic exploration on Monday. So today I'm going to actually start with a discussion of posterior sampling in deep RL. So as a quick reminder, in the world of bandits, posterior sampling amounted to maintaining a distribution over the bandit parameters, these thetas, right? So the thetas represent the parameters of the reward distribution. So if you know the thetas, then you know what the reward distribution for every arm is, and then you can just pick the best arm. But of course, the problem is that you don't know the thetas a priori, so you have to actually pull different arms, observe their rewards, use them to update your belief on theta, which I'm denoting here as p hat, and then somehow reason about those beliefs to decide which arm to pull. And posterior sampling or Thompson sampling prescribes a very simple way to use that belief to decide on which arm to pull, which is that you sample from p hat, pretend as though that sample was the true model, and act really with respect to that. So that was in the world of bandits. So now in the world of deep RL, we can ask, well, what is it that we're going to sample? So what do we maintain our belief over, and what do we sample? And how do you actually represent a distribution over that thing? So if theta denotes the parameters of, let's say theta denotes the probability that a given drug will cure or kill the patient, then it's pretty straightforward how you represent that distribution. You just have a bunch of numbers between 0 and 1. You can, let's say, maintain a beta distribution over them. That's all very straightforward. In deep RL, we'll have much more complex objects, so representing that distribution will be substantially less straightforward. So maybe to begin with, something I might ask is, well, Do you guys have any ideas for this? What are some things that we could maintain a distribution over, and how could we maintain those distributions to apply this idea to the deep RL setting? Any thoughts? Any ideas? So in the world of bandits, what we do is we maintain a distribution over models. So the model prescribes what reward you'll get for pulling each arm. What could we do in the world of deep RL that would be sort of analogous to that? Could we maintain a distribution over models for deep RL? Tough crowd today. Okay, that's all right. Yes?
Maybe we could train like multiple Q functions and then randomly sample like one Q function to sort of use on any time step.
Right, so you could, for example, maintain a distribution over Q functions. Why does it make sense to maintain a distribution over Q functions? Well, you can kind of say that if these are parameters of a reward model, maybe the equivalent in deep RL is a Q function model, because a reward model in a bandit tells you the total payoff you'll get from taking some action. The Q function in deep RL tells you the total payoff you'll get from taking some action. So the two seem somewhat analogous. Okay, that's one good option. Yeah.
For the ILQR, you could keep the regions where you apply the ILQR, and then you just sample where you are in the region.
Right. Yep. So so you could keep track of things like the model for ILQR. That's a very reasonable choice. Any other thoughts? So technically, if you really wanted to do Thompson sampling for deep RL, the truly correct, like textbook thing to do is to actually keep a distribution over MDPs. So in the world of bandits, these thetas fully define your model. In the world of MDPs, the whole MDP fully defines your model, meaning the transition probabilities and the rewards. Now that's oftentimes quite unwieldy, and it requires you to actually maintain not just one model, but many different models. So in practice, people often don't do that and do something more like the Q functions thing that was mentioned earlier. So in the bandit setting, the distribution over thetas is a distribution over the rewards that you would, it's basically a distribution that specifies the rewards you get for taking different actions. In RL, the Q function specifies the total returns you get from taking different actions. This isn't the only choice, and there are many reasonable choices that amount to Thompson sampling. So if you have a class of MDPs where keeping track of the model is tractable and reasonable, you could also very, very well do that. But what I'm going to describe is a method that keeps a distribution over Q functions, because this is one of the methods that appears in the literature, and it's a fairly simple way to apply this idea to deep RL. So the method is going to look like this. Step one, we're going to sample a Q function from some distribution over Q functions that we have, P of Q. And I'm going to tell you in a second how we maintain this distribution. Or I might actually ask you how you think we maintain this distribution. So you sample your Q function from P of Q. Then you act according to this Q function for one episode. Now there's an interesting point to be made here. How long should we act according to that Q function? And there's some trade-offs involved in that. If you act according to that Q function for exactly one step, then the trouble is that if your Q function distribution is very broad, you might, for the entire duration of that episode, you might not act according to any well-defined Q function. So basically your behavior might be no better than random exploration. But if you stick to the same Q function for the entire episode, then you might do something a lot more coherent. If you want to think of an example, let's say that you, this is maybe something I can draw on the board. Let's say that you live on a different marker. Let's say that you live on a one-dimensional number line, right? And you start off here. This is 0. And you're not sure where the rewards are. Maybe they're on the right side or on the left side. If you pick one of these two models and stick with that model for the whole episode, you will either go all the way to the right or all the way to the left. But if you change your mind every single time step, then you might do something like this. You might walk around randomly. So picking a model or a Q function and sticking to that choice for an extended period of time enables this is sometimes referred to as deep exploration, meaning that your exploration strategy remains coherent, which means that you can progress through the state space a bit further instead of doing essentially a random walk near the start. So it's quite important actually for this method to work well to keep acting according to that same Q function for an extended period of time, and a very convenient choice there is to do one episode. There's a question?
So what if you, instead of having many Q functions, you have only one, but then you have some noise parameter, and you try to estimate that parameter?
Right, so the comment was, what if instead of having one Q function, or sorry, what if instead of having a distribution over Q functions, you had one Q function, and then you would add different kinds of noise to it? That's actually a very reasonable way to maintain this kind of distribution. The two are actually the same. You can say that if you have one Q function and different kinds of noise, that is the same as having multiple Q functions. It's just a different way to represent it. And there are actually methods that do exactly this. I won't cover them in today's lecture, but it's actually a follow-up to the paper that I will cover. Yes?
For any given Q, like in tabular case, for a given Q function, can you invert it to get a reward function that it's trying to describe?
Is it possible to recover the reward function that a given Q function is describing? Yes, it is. If you know the transition probabilities. And you can work this out on paper. If you know the policy and you know the transition probabilities, you can just solve for R. Okay, so step 2 is act according to Q for some extended period of time, and one episode is a very convenient choice. Step 3 is update P of Q. Update P of Q basically means update your Q functions, and because you have a distribution over Q functions, you update the whole distribution. And then you repeat. So this describes a complete reinforcement learning procedure, but we have to actually figure out how we're going to keep track of P of Q. So our Q functions, since we're doing deep RL, our Q functions are themselves deep neural networks. So how can we maintain a distribution over deep neural networks? Any ideas? Yes?
Would a Bayesian network work good for this?
Okay, so one answer is we could use a Bayesian neural network. So in those of you that watched the variational inference lecture might already guess how this could be done. You could do variational inference and maintain a distribution over parameters of your neural networks, and then sample from the distribution over parameters. That's a very reasonable choice. Any other ideas? Where have we seen distributions over neural nets before? Yeah.
There was also the bootstrapped one that we used for the risk aversion.
Right, so back when we talked about model-based reinforcement learning, we discussed how we might want to maintain a distribution over models for model-based RL. In fact, if we did Thompson sampling with models instead of Q functions, we could use exactly that technique. And at the time, the way that we did this was by using the bootstrap. And using the bootstrap basically amounts to training multiple different models on resampled versions of the same data. And that can be shown to be an approximation to the posterior over the models given the data. So that's in fact the method I'm going to describe next. But a quick comment before I do that. One of the reasons that this whole thing works is because when you are doing Q learning is an off-policy algorithm. So even though in step 2 you act according to one specific Q function, the data that you collect in step 2 can be used to update your entire distribution of Q functions because Q learning is an off-policy method. So if you were doing, let's say, policy gradient, this would be potentially a lot trickier. Okay. So we're going to use the bootstrap to represent the distribution over Q functions. As a reminder, the way that this works is that if you have a data set D, you can resample that data set with replacement n times to get a new set of data sets D1 through Dn. So resample with replacement essentially means that each of your data points gets a little counter, an integer counter between 0 and n. So if my initial data set is, let's say, x0, x1, and x2, so I have this really small data set, and that's my D. Then when I generate D1, what I will do is I will also have 3 data points, and I will select for each of them one of these 3 with replacement. So maybe for data point 0, I generate a random integer between 0 and 2, and I get x1. And then maybe for the second data point, I generate a random integer between 0 and 2, and maybe I get x1 again. And then maybe for the third one, I get x0. So now my first data set is x1, x1, x0, which is the same as putting counters on these, counter of 0, 2, or counter of 1, 2, and 0. And then I repeat. So data set D2, maybe I'll end up with x2, x0, x0, etc. Now, the crucial thing about this resampling procedure is that the distribution over data points in each of these data sets is exactly the same, but the particular data points that constitute each data set might be different. And then all you do is for each of those data sets, you train a completely separate model, f theta i. And it can actually be shown that if you follow this procedure and you have enough of these bootstraps, then the set of thetas is a good approximation to the posterior over parameters. So then if you want to sample from your distribution over models, since you're approximating that distribution with this discrete set, all you actually do is you sample an integer between 1 and n, and then use the corresponding model f theta i. So the particular method that I'm going to discuss here is covered in this paper called Deep Exploration via Bootstrap DQN by Ian Osman et al. And one of the things that they illustrate in that paper is how a bootstrap ensemble of neural nets compares to a Gaussian process. Gaussian processes are often used as a kind of gold standard for Bayesian regression, for low-dimensional problems at least. And when you see a plot like this, the way that you read it is that the shaded regions represent the variance. So when you see these bigger shaded regions, that means that the function approximator is estimating that there's larger variance in that region. So the Gaussian process picture makes a lot of sense. Near the data points, near these blue dots, it's very certain about what the function is. And far away from the blue dots, it gets broader and broader. The neural net, its variance changes a little bit differently. So its variance actually blows up a lot out on the tails, but it does something fairly similar here in the middle to the Gaussian process. So this kind of suggests that there's some reasonable uncertainty estimation going on. Okay, now there's one little problem with this scheme. If you remember how homework 3 went, you had to train convnets to play Atari games. Now if you imagine that instead of training 1 convnet, you had to train, let's say, 20 convnets, you might have trouble finishing your homework on time. So the fact that we have to now train many models should perhaps be cause for concern for us. So training n big neural nets is rather expensive. It's not impossible, and we could do it, but it would be much nicer to try to avoid that. So Osman et al. Actually proposed a solution to this. What they propose to do is to not have n totally separate neural nets, but to essentially have one neural net encoder with multiple heads. So intuitively, you can think of this as saying that there is one convolutional stack that takes in your images and featureizes them, and then multiple heads that all use the same features to output different Q values. It's a fairly reasonable way to train your ensemble. Kind of all bets are off as far as what it will do, because in principle that convnet could do all the work and then the heads could just be identity functions. But in practice, that doesn't tend to happen, and you actually do get decent uncertainty estimates from sharing many of the parameters, so long as you have separate heads at the top. And of course, this saves you massively in terms of the amount of computation that you have to do. There's another detail that I should mention, and I mentioned this also when I talked about bootstrap ensembles in model-based RL, which is that this resampling with replacement procedure is necessary in theory, but it's not really necessary in practice. So in practice, because neural nets themselves use highly randomized training procedures, it turns out that even if you omit this resampling with replacement step and simply copy D n times to make n perfectly identical copies of your data set, but you initialize your neural nets at random and train each of them with SGD, obviously with different random seeds, it turns out that that already will diversify your networks enough, and the resampling with replacement in practice doesn't actually make any difference for deep nets. But again, it's one of those things where it works in practice but not in theory. So if you want to tell somebody what you're doing, if they're kind of a little bit more mathematically inclined, you say, well, you meant to do resampling with replacement but forgot to code it up. But if you just want to know how to do it in practice, you can pretty much forget this first line and just do everything else. All right, any questions about this stuff? Yeah?
So you do sampling over the parameters of the network, right? There's P theta.
Yes, so when you sample a model from P of Q, what you're really sampling is the thetas from your distribution over thetas, which is defined as a mixture of Dirac deltas and separate Dirac deltas.
Oh, okay.
So if you want to actually write out the P of theta, the way that you would write it out is this. You would say that P of theta, and this is exactly the equation that was in the model-based RL lecture, is equal to 1 over n, sum I equals 1 to n, of the Dirac delta theta equals theta I. And of course, we can argue about how well a mixture of Dirac deltas approximates some really complicated distribution, but you can sort of pretend that if n is big enough, this will be good enough.
Because you could sample each parameter individually.
Yes, so you could sample each parameter from a different mixture element, but that might be kind of bad news because neural nets have a lot of internal symmetries. So the different parameter vectors might not have anything in common with each other. They might actually represent very similar functions in very different ways. So if you start mixing and matching parameters, you might get garbage functions out of this. Yes?
In practice, how well does just like a lot of dropout do?
Right, so the question was, in practice, how well does a lot of dropout do? It's not bad, actually. So in fact, dropout is one of the ways that you can approximate Bayesian neural nets. So there's a very well-known paper by Yar and Gall that argues that dropout with some careful design choices can actually be used to approximate a variational distribution modeling the posterior. And then the way that you train it is you literally just do dropout. From my experience in practice, the bootstrap tends to be a little bit better behaved, but your mileage may vary. Okay. So why does this whole thing work? Why is this a good idea? Well, if you explore using random actions, the trouble is that you tend to kind of oscillate back and forth. You do a random walk, which might not go to a coherent or interesting place, kind of like that picture I had with the number line on the board before. So, for example, here's a sort of a classically difficult exploration problem. This is the Atari game Sequest. And Sequest is a game about an ecologically irresponsible submarine that is supposed to kill fish by shooting torpedoes at them. And if its fish-killing rampage takes too long, then it runs out of oxygen. So this little oxygen bar at the bottom shows how much oxygen is left. And when the submarine runs out of oxygen, it will die unless it goes to the surface. And so the reason that this is a difficult exploration problem is that if you wander down to the bottom of the sea while shooting all the fish, you are very unlikely to reach the surface just through random actions. So if you imagine that every time step you randomly go up or down, you become exponentially unlikely to go all the way to the top the deeper down you are. So that means that just an epsilon greedy strategy might very rarely discover how to surface the submarine. If you explore using random Q functions, then so long as you occasionally sample a Q function that prefers to go up, you're much more likely to actually surface the submarine, at which point you would realize that bringing the submarine to the surface is a really good idea because it allows you to refill your oxygen meter, which prevents running out of oxygen. Now in practice, the benefits that you get from doing bootstrap DQN are a little bit mixed. So this is a comparison on 6 different Atari games. The green line shows regular Q-learning. The red line shows this bootstrap method. And you can see that it helps, although sometimes it helps very little. Sometimes it helps a bit more. In general, the trade-offs with this kind of posterior sampling style exploration method is that it's good in the sense that it doesn't involve any change to the original reward function. So when we talked about exploration bonuses with novelty, you have to actually change your reward function, which means that you're biasing your policy to do things that are different than just maximizing reward. Here there is no change to the reward function, which means that all of those Q functions in your P of Q are all trying to actually accomplish the task, just in slightly different ways. The downside is that in practice, very good exploration bonuses tend to do better than this particular strategy. So the exploration bonuses bias your policy a bit. They involve a bit more tuning because you have to actually select the coefficient on them and make a bunch of other design choices. But if tuned properly, the exploration bonuses do tend to work a bit better. All right. So now let's talk about the third category of exploration methods for deep RL, which are methods based on information gain. So when I talked about bandits, I introduced this notion of information gain, which is essentially a quantification of how much you learn about Z from taking action A and observing Y. And then, of course, if we want to instantiate this method, we have to choose what Z should be and what Y should be. So we saw for bandits, a reasonable choice would be to make Y be the reward, because that's what you observe after taking an action, and you could have Z be the parameters of the reward. So then you're saying, let me try to figure out the action that will allow me to learn the most about the parameters of the reward function. So of course, if you want to apply this idea to deep RL, you have to answer the question, information gain about what? What do we want to actually learn about? Any ideas about what do we want to learn about when we do exploration in deep RL? Yeah.
Like how much reward different states and actions.
Right. So one interesting choice is to learn about the reward. It's an interesting choice. However, in practice, it kind of seems like a very natural thing. In practice, it doesn't tend to work so well, and here's why. If we have a very difficult exploration problem, then your reward function might be rather sparse, meaning that maybe your reward function is kind of zero everywhere, and just in a few places it's large. And what that means is that for most actions, they will not actually learn anything about the reward. And in fact, you might not even have an action available to you that learns anything about the reward until after you've taken a really long sequence of other actions. So while in some sense information gain about rewards is the thing that you ultimately want to do, it's actually very difficult to craft useful exploration methods out of information gain about reward because it's so hard to get information gain about reward. Now another maybe slightly peculiar choice is to say that you want information gain about state density. It's a bit strange, but it actually makes a lot of sense. Now, it takes us a second to really understand what it means to gain information about state density, but intuitively, what it means is that you want to take actions that will change your belief about P of S. Now, what will change your belief about P of S? Well, visiting states that you've never visited before is one of the main things that will change your belief about P of S. So if you visit some totally new state, then your P of S will change drastically, which means that you've gained a lot of information about P of S. If you visit a state that you visited 1,000,000 times before, and now it'll have been visited 1,000,001 times, your P of S will not change very much, which means you will not have a lot of information gain. So while at first it seems kind of weird to like learn more about which states you visited, because shouldn't you already know which states you visited, in practice you can actually design exploration methods out of this idea. And then another thing that you could do is you could have information gain about dynamics. You could say, well, will taking this action allow me to learn more about P of S prime given SA? And that's convenient because you always have dynamics. Every single transition has dynamics. So while the dynamics are not really what you want, because you can probably solve the MDP without learning the dynamics well, in practice it turns out to be a very convenient thing over which to reason about information gain. But it's still a bit of a heuristic. Okay, now regardless of what you pick here, it is generally intractable to do exact information gain. So as with all things in deep RL, if we want to actually use this in practice, we're going to introduce sort of approximations on top of approximations to try to make this actually practical. there are a few different approximations we could use. One fairly crude but effective approximation is to do what's called prediction gain. Prediction gain is not quite information gain, but it is closely related mathematically. And it's often used on state densities. So the equation for prediction gain is the difference between the log probability of S after you've seen S minus log probability of S before you've seen S. So you have some p theta, you observe a new state S, you update p theta to get p theta prime, and now, presumably under p theta prime, this S has higher probability, and then you can take the difference of those two things. And I won't go into it in this lecture, but there's a kind of a crude mathematical relationship between this and information gain. But at an intuitive level, what this is saying is if your log probabilities changed a lot, then you probably visited some interesting state. If your log probabilities changed very little, then you probably didn't learn anything new. And this is essentially the principle that the count-based exploration is based on, and it was also used in a number of previous works. So if the density changed a lot, the state was novel. So before, I basically motivated this from the standpoint of just seeking novelty, but you can also motivate it from the standpoint of information gain, albeit somewhat crudely. Now, another thing you could do is you could apply the framework of variational inference to estimate information gain. And that's what I'm going to talk about for the rest of this section, which is based on a paper by Huthoft et al. Called VIME, Variational Information Maximization for Exploration. So the first identity that is useful to us here is that information gain can be equivalently written as the KL divergence between P of z given y and P of z. So P of z given y is your distribution over z, the thing that you want to learn about, after you observe y. And P of z is your distribution over z before you've observed y. Now, after you observe y, P of z given y is going to have lower entropy than P of z. Like, getting more evidence makes you more certain in the right answer. It never makes you less certain. So that means that the difference between P of z given y and P of z, essentially how different those distributions are, is a measure of how much you've learned about P of z, because P of z given y is only going to get more concentrated. And in fact, you can actually show with a little bit of algebra that this is exactly equivalent to information gain, yes?
Couldn't you be overestimating the value, and then you explore it, and then you realize that you actually don't know?
Could you be?
Sorry, if you're overconfident about.
Oh, you're saying does this thing actually get more peaked?
Can entropy increase after seeing something? Like if you're overconfident and what you thought happened didn't happen, and so now you realize that you don't know anymore.
I don't believe so, but I need to get a piece of paper and check. Okay, so I'm going to instantiate this idea in the context of information gain about transitions, about dynamics. Although very similar math could be used to also derive a version of this for information gain about state distributions or even about reward distributions. So the basic idea will actually be the same. So we'll say that there's something that you want to, some kind of quantity of your MDP that you want to learn about. In this case, it'll be the transitions. And that quantity will be parameterized by theta. So if you want to learn about transitions, then you have p theta st plus 1 given stat, and theta is the thing that you want to learn about. So theta is the parameter vector for the quantity of interest, in this case the transition probabilities. But you could just as well have p theta of rt given stat, or even p theta of st. It turns out that actually the derivation will look very similar in all these cases. So the thing that you want to learn about, the z, is going to be the theta. And the evidence that you observe, the y, is a transition. It's an st plus 1. So we want to approximate the information gain about theta from observing st plus 1. And we know that information gain is equivalent to the scale divergence, so what we're going to actually try to do is estimate the scale divergence. So if we substitute in our definition of z and theta, here's what we get. We have the KL divergence between p of theta, which is the model parameters, given our newly observed transition, and given the history of all prior transitions. right? So we've gained one transition, but we also have all the transitions we've seen before. So the KL divergence is between theta given the history and this new transition versus theta just given the history. So the intuition here is that a transition is more informative if it causes your belief over theta to change a great deal. And now, of course, maintaining a full distribution over your parameters, if you, let's say, have a neural net representing your transition probabilities, is going to be intractable, just like before. So we're going to do some kind of approximation. We could do the bootstrap ensemble here as well. We're actually going to try to do variational inference this time. But again, there are probably many different ways to instantiate this. The particular method used in the Huthoft et al. Vine paper is to use variational inference. So when you use variational inference, you introduce some other parametric distribution that we're going to call Q, and it has some other set of parameters phi, and it's trying to approximate p theta given h and p theta given h, comma, st, at, st plus 1. So when you observe a new transition, you update the variational parameters phi to get a new vector of variational parameters phi prime, and then compare q of theta given phi prime and q of theta given phi. All right, so that means that we're going to end up optimizing a variational lower bound in order to actually train q theta given phi. So this is the variational lower bound that you've all seen in the variational inference lecture. It's just the KL divergence between theta given phi and your likelihood, p of h given theta times p of theta. So p of h given theta, that's basically the likelihood that your model assigns to all of your transitions in your history with the parameter vector theta. And p of theta is some uninformative prior on your parameters, like a zero mean Gaussian. Now, you have to choose what your q of theta given phi is. And for deep neural nets, unfortunately, you can't be too picky because theta is extremely high dimensional. So typically what people do is represent it as independent Gaussian distributions over each parameter with mean phi and maybe with a variance. And the variance can either be learned or fixed. So this is the same as what I discussed when I talked about distributions over parameters in the model-based RL lectures. In a regular neural net, you have a weight on each connection. In a Bayesian neural net, you have a little distribution over weights on each connection. And the distribution here is going to be Gaussian and independent, which means that the probability of theta is just a product of independent marginals over theta. And each of them is Gaussian. So if you want kind of a quick crash course on this, check out this paper by Blundell et al. Called Weight Uncertainty in Neural Networks that describes a very simple framework for Bayesian neural networks. Okay, so we're going to use this as our framework to train our distribution over neural net parameters. And when we're given a new transition, SAS prime, we're going to update phi to get phi prime. So we're going to take the means and variances for each of our weights, and we're going to update them by running some more gradient descent to get new means and new variances phi prime. So this basically corresponds to training the network on your data set, including this new transition. And then you're going to use the KL divergence between q of theta given phi prime and q of theta given phi as your approximate bonus, because you know that q of theta given phi approximates p of theta given h, and q of theta given phi prime approximates p of theta given h, st, at, st plus 1. And because this thing up here is information gain, this thing down here is an approximation to information gain. And then we can use this as an exploration bonus, just like we did when we talked about pseudo counts. So long story short, every time you observe a new transition, update your phi to get phi prime by training on that new transition and your past history, and then use the KL divergence between the new and old parameter distributions as your bonus. Yes?
When we're doing information bonus techniques, do we add this bonus during training, but then during evaluation we remove it?
Right, so the question is, when do we add this little exploration bonus? You add it during training. At test time, there is no, the reward doesn't matter during test time because you're just running your policy.
Or you use it to evaluate how good your policy is doing, still use.
Oh, I see. Right, so if you want to evaluate how well your policy is doing, then you would, of course, omit this because you want to evaluate how well your policy actually does on the reward of the task. There's a question here.
you're trying to learn, if you're trying to adjust the dynamics, but you add this term to the reward function when computing the actions. The actions are computed using your dynamics model, right? Like the p.
Ah, okay, okay. So the question was, are you using your dynamics model to compute your actions? So this is an interesting question. In this particular paper, the RL method they use is actually a model-free RL method. So even though they learn a dynamics model, they're not actually using that dynamics model to make decisions. They're learning the dynamics model purely as a mechanism for exploration, which is a little peculiar. Now, that said, you could also do model-based RL and use this technique. In model-based RL, things get a little more complicated because in model-based RL, you have to actually plan to visit new states. So in model-based RL, what you would do is you would calculate this quantity in expectation over possible future states you might get to. And there are actually methods that do some variant of this. And you can use that scheme to do exploration in model-based RL, which is very convenient because in model-based RL, you would probably already be maintaining a distribution over models. So that's not what's done in this paper, but it's a good idea to do that. Any other questions? Yes?
Sorry. I would have thought that they would have kept the distribution over the policy. Is that?
Yeah. So could we keep a distribution over the policy parameters? I think you probably could. It's interesting. So I haven't seen a method that actually does this. So I'm not sure what would work well or what would work poorly there, but I could definitely imagine, for example, a policy gradient algorithm that maintains a distribution over policy parameters and then looks at information gain over policy parameters. I would imagine that you would get high information gain when you have trajectories with very different rewards, because then you have a big gradient. So I could actually imagine that could work well. I've not seen any papers that do this, though.
Just out of curiosity, when you say policy parameters, are you talking about the weights of the neural network or like the mu and sigma?
The weights of the neural network. Yeah. So every time I say parameters here, I'm referring to the weights of the neural network.
Could you also do it over the mu and sigma?
You could. I mean, in a sense, there's a choice to be made in terms of the parameterization that you care about, and different choices of parameterization will actually change these quantities. So you could do it over mu and sigma. You could do it over some function space representation of your policy. Those are all reasonable choices. Okay. So here are some of the comparisons in that paper. Here let me see which one is which. Okay, the blue plots show the a regular policy gradient method, and then the orange plots show the same policy gradient method, but augmented with this information theoretic exploration technique. So some trade-offs about information gain. Arguably provides an appealing mathematical formalism because it sort of perhaps seems a little bit more principled in terms of reasoning about gain in information over some quantity, although that quantity is not necessarily the quantity that you actually care about. The downside with these kind of methods typically is that including the model does add some degree of complexity, and it's generally harder to use them effectively because with that additional complexity, including things like variational inference, you end up with a lot of additional hyperparameters, and choosing those carefully becomes harder. So in practice, it's a little tougher to use these methods very effectively. Now, that said, there are even more heuristic simplifications of this kind of general scheme that also tend to work very well. So, I talked about arguably the more sophisticated version of this, where you do something that approximates information gain. But you could also kind of go back to the picture that I had before, where essentially, if you have any function represented by this green line, you're trying to estimate that function using a neural net represented by the orange line, then you'll get larger errors further from the data and smaller errors closer to the data. So you could sort of discard this whole notion of information gain, still deal with transition probabilities, and just look at errors in fitting your transition probabilities. And that would already give you a decent heuristic for determining whether you're close to the data or not. And people have done that before. So, for example, in this paper by Stady et al., they encoded image observations using an autoencoder, and then build a predictive model on the autoencoder latent states, and then use the error of that latent space dynamics model as their exploration bonus. In this paper by Schmidt-Huber et al., they used an exploration bonus for model error, they also introduce actually an exploration bonus based on the model gradient. So in VIME, the bonus is based on how much the model changed. You can also think of the gradient as crudely approximating how much the model changed. If the gradient was big, that means that your model changed a lot, so that might indicate a novel transition. And many other variations. And there are many, many other papers that do some variant of looking at model errors as a way to do better exploration. Okay, so to briefly recap the class of exploration methods in DeepRL that we talked about optimistic exploration, which is exploration with counts or pseudo-counts. You have different choices for the model of your densities, and these kind of methods tend to actually work quite well, although they do have a few hyperparameters. We talked about Thompson sampling style methods, which maintain a distribution over a model of something. So, for example, a model of Q functions. And if your models are represented by neural nets, then a very convenient way to do this is to use bootstrapping. And then we talk about information gain style algorithms, which are intractable to do exactly, but if you do something like a variational approximation, then you can get decent approximate information gain. And if you do it, for example, in transition probabilities, then you can get some pretty effective exploration out of that. If you want to learn more about this stuff, here are some suggested readings. So this is a fairly early paper that introduces a variety of somewhat heuristic but interesting exploration methods. This is the paper on with the autoencoder. This is that bootstrapping paper, the posterior sampling paper. This is the paper that does information gain. This is the count-based paper that I mentioned on Monday. And these are a couple of other things that I mentioned in the context of exploration bonuses. All right, so we're going to take a short break. And then after the break, I'll talk about how imitation learning can be incorporated into RL to further address exploration challenges. So we'll be back at 11 o'clock in 3 minutes.
Hey, have you seen any work that talks about how model errors are affected by different types of autoencoders? So for example, like just your vanilla one versus like the beta VAE that leads to disentangled latent states. Because one of my ideas is that both of them explain the same thing, but it seems like a disentangled version or other work better.
So I haven't, and I think part of the difficulty with comparing these things is that if what you want is the highest likelihood fit for your model, then the best thing to do is to optimize a bounding or likelihood. So the way that you optimize a bounding or likelihood is you set beta to 1, you learn the output variances, and that's that. Anything other than likelihood, you have to deal with this weird issue of like, well, okay, you get a more disentangled representation. In what way is that better? Like, is it generalizing better in some setting or something like that? So it may be that it is better in some ways, but there are ways that are a little difficult to quantify sometimes.
Okay.
So yeah, the answer is that, to my knowledge, nobody really knows.
Yeah, thanks.
So things like well, I guess you do. Given your PhD research, it didn't make sense, but things like false discovery, like divergent hypothesis testing is never talked about at any level. Like false discovery. It's a very new idea, like that your own hypothesis testing is not in 2000. Yeah, it's not something to talk. I mean, it will be in 20 years, but not right now. And it's very important in given the new way that we do testing. We're not testing one thing, we're testing 10,000. It's very useful.
All right, let's continue.
Yeah.
So before the break, I talked about exploration methods for DeepRL kind of in the classic setting where you don't have any other knowledge other than what you observe through exploration. In the remainder of today's lecture, I'll actually talk about how we can do a better job of solving difficult exploration problems by introducing some additional knowledge in the form of demonstrations. So in this class so far, we've talked about imitation learning, and we've also talked about reinforcement learning, and they have some different trade-offs. So obviously, imitation learning requires demonstrations, but reinforcement learning requires reward functions. imitation learning has to deal with this distributional shift problem. So if you just do naive imitation learning via behavioral cloning, that doesn't necessarily address the distributional shift issue, and you might get very poor performance. And we talked about ways to mitigate that. But reinforcement learning has to address the exploration problem, which means that you have to actually have some way to discover the high reward regions of the state space, which of course imitation learning doesn't have to worry about because the demonstrations give it the right behavior. Imitation learning is convenient because it's often simple and stable, whereas reinforcement learning algorithms can be a little tougher to get to work well, as many of you might have learned in the course of doing your homework. And of course, imitation learning is only as good as your demonstrations, whereas reinforcement learning, because it's actually optimizing your final measure of success, your reward function, it can become essentially as good as possible in your environment. So that's perhaps very appealing. So can we somehow combine these two ideas? So we can try to get the best of both. We can also perhaps undesirably get the worst of both if we're not careful. So we have to consider how to properly do this. So what I'm going to discuss is a setting where you have both demonstrations and rewards, and how you can make use of both of those things to kind of get both something that overcomes exploration challenges and something that can become arbitrarily good even if your demos aren't perfect. So to briefly recap, in imitation learning, we saw that we have data that consists of observation action tuples, and then we run some kind of supervised learning on that data to get our policy. And we saw that this could be used to solve a variety of interesting problems, from driving cars to flying quadrotors. And in reinforcement learning, of course, you have an agent that interacts with the environment and learns entirely from rewards. So let's say that we have both demonstrations and reward functions. What can we do with that? So one thing that we could try to do is we could address distributional shift in imitation learning. Now, we actually already saw methods that address the problem of distributional shift in imitation learning when we talked about inverse RL. So even though the behavioral cloning method does suffer from distributional shift, inverse RL generally addresses this problem because inverse RL actually has a reinforcement learning step embedded inside of it. So in a sense, inverse RL already combines reinforcement learning with imitation because it's doing kind of regular forward RL when it's learning the policy, and then it's using the demonstrations to get the reward function for that policy. But inverse RL doesn't actually use a known reward function. So the point of inverse RL is typically that you just have demonstrations, you don't have a reward, and you want to imitate those demonstrations in a way that doesn't suffer from distributional shift, or you want to recover the reward function that explains those demonstrations for some kind of downstream analysis. Now, if you have both a reward function and demonstrations, you could actually try to use both of them. One of the simplest way to use both of them is to simply pre-train with imitation learning and then fine-tune with RL. In fact, it's very, very straightforward to implement, and you guys could, for example, try it by just taking your homework 1 solutions and fine-tuning them with RL a little bit. And this can actually work pretty well because the demonstrations can overcome exploration challenges, because the demonstrations show you how to do the task well. So if your initialization is effective, then your policy might already start off going to good regions of the state space, and the subsequent RL fine-tuning might get it to go there more consistently or more quickly. So the procedure is very, very simple. You simply run behavioral cloning, and then use that as a starting point to run reinforcement learning. So you collect your demonstration data, initialize your policy by doing maximum likelihood training on your demonstration data, then run your policy to collect some experience, improve it with any RL algorithm, and then repeat steps 3 and 4 until you're happy with the performance of your policy. Here's a little video of a paper by Katrina Mulling showing the demonstration collection phase. So this is a paper on getting a robot to play ping pong. And oftentimes demonstrations in robotics require a little bit of operator expertise. So here Katrina is demonstrating how to get the robot to return the ball. This was used to produce some demonstrations, which were then used to initialize the robot with imitation learning so that it could at least occasionally return the ball successfully, which was enough to then get a reinforcement learning procedure bootstrapped so that it could actually learn the task consistently. Now, this procedure, even though it's very simple and very reasonable, does have some pretty major flaws. Does anybody have any thoughts about how this could go horribly wrong? Yeah.
Seems like you could really bias the agent into doing something that's only locally optimal.
Okay, yep. So one possible failure mode is that maybe step 2 might result in a very deterministic policy that goes to a very specific region of the state space, never does anything else, and then your agent might essentially get stuck. So you might actually end up with a worse solution than if you ran RL from scratch. Any other thoughts about bad stuff that could happen? Yeah.
We could end up with that annoying thing in RL where our graph just starts to tank at the very end.
Can you expand on this a little bit?
When it doesn't necessarily stay stable, and then it ends up not doing so well in the very end.
So you could definitely inherit essentially all the usual issues with RL, right? So anything where steps 3 and 4 involve running an RL algorithm has all the downsides of RL. So one might argue that in some ways this actually combines the worst of imitation learning in RL, because you're running RL essentially without any additional crutch, and you're running behavioral cloning at the top without any additional fix for the distributional shift. So you might end up with the worst of both. One thing that we can look at to maybe help us think about some of the issues here is to compare this to what Dagger does, right? So Dagger trains a policy on a bunch of human data, runs that policy, relabels the experience from that policy, and aggregates it so it actually combines the initial data and the additional on-policy data, and then trains on the whole thing. Now, compared to Dagger, this kind of pre-training and fine-tuning approach actually does have a major issue, which is that if your initialization here in step 2 is not very good, like maybe it suffers from some distributional shift and performs much worse than the demos, then you will essentially forget about your demos in steps 3 and 4. So if, let's say, you have a trajectory of length 100 and you make a mistake on the 100th step, then it doesn't really matter. But if you make a mistake on the first step, the remaining 99 steps will be garbage. And while RL will still do its thing and RL will still improve your policy, you're getting a very minimal benefit out of that initialization because it's failing at its primary purpose, which is to provide you with that good exploration. In contrast, Dagger is retaining that initial data set and keeps training on it again and again. So with Dagger, even if you initially fail to properly imitate your demonstrations, you'll still keep them around and you'll keep reusing them. So one of the things that we can think about at this point is, well, can we modify this procedure a little bit so that we keep the demonstrations around and still use them even while we're doing RL, so that if we failed to imitate them properly in steps 1 and 2, which could definitely happen because of distributional shift, we would still get the benefit of those demonstrations later down the line. Okay. So the problem is that our initial pi theta can be very bad due to distributional shift, which means that the first batch of very bad data that we collect, that we then run RL on, might destroy that initialization, and we wouldn't get any of the benefit of it. So how can we avoid forgetting the demonstrations? One thing we could do is use off-policy reinforcement learning. So with off-policy reinforcement learning, we could include the demonstrations in the buffer. So off-policy RL can use any data, which means that if you let it use these demonstrations as essentially off-policy samples, you can keep them around for the whole training process, and it might still mitigate the exploration challenge because those demonstrations would presumably have larger rewards than the experience you gather with a totally random initial policy. So since the demonstrations are provided as data at every single iteration of RL, they're never forgotten, so they can keep being used. But the policy can still become better than the demos because it's not forced to actually mimic them perfectly. It just has them in the buffer, and if they're useful, it'll use them. If they're not useful, it will not use them. So there are a couple of ways you could do this. You could do it with off-policy policy gradient using importance sampling, and you could also do it with off-policy Q-learning. So let's talk about the importance sampling version first. So this requires us to think back to what we covered way at the beginning of the course when we talked about policy gradients. So if you recall, when we have policy gradients, if we have data that did not come from our current policy, we need to reweight it by multiplying it with an importance weight. And the correct importance weight actually involves a product over all the time steps. And we talked about how if we have data that's close to on policy, we can approximate this by only using the importance weight at the current time step. But if the data is very far off policy, you do have to use the full product. And in general, your demonstrations might be very far off policy. Now, there's an argument to be made that if you first behavior clone your demonstrations and then do this, maybe they're not that far off policy, and maybe you can still use only the weights at time step t, and that could be an interesting thing to try. The method I'm going to cover right now actually does use the full product, which causes some issues, but it still works decently well. So when you take the sum over your samples, you include both your demonstrations and your recent experience in your sample batch. And we might ask, well, other than the intuition about demonstrations addressing exploration challenges, is there some more mathematical reason why this would be a good idea? Don't you want on-policy samples? If you could just get more on-policy samples, wouldn't that give you a better gradient estimator? So an interesting kind of principle that we can draw on to motivate why we want to include demonstrations in a policy gradient estimator is the optimal importance sampling distribution. So it turns out that you can actually derive the optimal distribution to use for importance sampling to get the lowest variance estimator. So let's say that you want to estimate the expectation of f of x under some distribution p of x with importance sampling. So you're drawing your samples from q of x. You can actually figure out which q of x gives you the lowest variance. And it turns out that the answer is that the lowest variance comes from setting q of x to be proportional to p of x times the absolute value of f of x. This is actually fairly intuitive. If f of x is really big somewhere, then you want to include the samples where f of x is big. If f of x is close to 0, then those numbers that are close to 0 will not affect the expectation very much, and it's okay not to include them. So because the quantity inside the expectation is the reward, this actually motivates using a distribution that has higher reward than your current policy, because it might actually be closer to this optimal importance sampling distribution. Now, of course, what we're actually going to do is not the optimal distribution, but this is a somewhat hand-wavy argument for why using distributions other than the on-policy distribution might actually give you a better gradient estimator. So the best sampling distribution should have high reward. It should also not be too far from your policy, but presumably your policy is improving, so as you train your policy, it'll become closer to high reward distributions. So if your policy looks like this, but then you have high reward over here, you might actually prefer to skew your samples to oversample this peak because it has high reward. So you can crudely think of including demonstrations in your policy gradient estimator as doing some variant of this. Okay, so now how do we construct this sampling distribution? There's a little bit of a catch here. So the first problem is, which distribution do the demonstrations come from? Right, so you know which distribution your experience came from because you ran your policy, but you don't actually have access to the policy of the demonstrator. So using importance sampling with demonstrations is a little bit non-trivial because you have to actually figure out what distribution the demonstrations came from. And there are a couple of choices that have some downsides. So one option is to use regular supervised behavioral cloning to estimate pi demo. So you don't know what pi demo is, but you could regress from S to A on your demos and essentially estimate pi demo. Now it won't be a great estimate, but it might be good enough to produce sensible importance weights. Another option is to simply assume a Dirac delta distribution. So you estimate your pi demo as a mixture of Dirac deltas for every single demonstration in your data set. This is also pretty reasonable, although you really want to make sure that you use self-normalized importance sampling. So self-normalized importance sampling is where you divide by the sum of the weights. Technically, if you look up importance sampling in a textbook, you'll see this formula. So you take the ratio of P of x and Q of x and multiply by 1 over n. Self-normalized importance sampling multiplies by 1 over the sum of the weights, essentially ensuring the weights sum up to 1. And this is important if you use these Dirac deltas, because if, let's say, you have continuous actions, then your policy probabilities are likelihoods from a Gaussian. These Dirac deltas are going to be 1 divided by some integer. So those numbers aren't really comparable. Okay, there's a second problem, which is that your experience here, this D, actually comes from multiple distributions, right? Because it includes demonstrations and it also includes the experience from your policy. But importance sampling is meant to work with a setting where you have one distribution, Q of x, that you drew your experience from. So if you really want to do this correctly, what you have to do is you have to use something called a fusion distribution, meaning that you have to set Q of x to be an average over all the distributions that you drew data from. Now, using a fusion distribution, if you have data from a policy and a bunch of Dirac deltas, is pretty easy because all of the data from your policy has 0 probability on Dirac deltas. But if you do option 1 and use PyDemo, you do actually have to calculate the probability of every one of your trajectories under both PyDemo and your recent policy, and then mix those together. Okay, so here are a few animations from the paper that does this thing with demonstrations. This is actually a sequence obtained from motion capture of a person running that is then included into a policy gradient procedure to learn this kind of humanoid running behavior. All right, so that's how we can include demos into policy gradient with importance sampling. Now the other class of methods that I mentioned is Q-learning algorithms. Q-learning algorithms are actually reasonably straightforward to use with demonstration data because there all you really have to do is just drop the demonstration into the replay buffer. But there are a few important caveats that are important to make this work well. So the good news is that Q-learning is already off policy, so you don't need to bother with importance weights. So the obvious thing to do is to just drop them into the buffer, which means that you just modify your Q-learning algorithm so that you just initialize your buffer at the very beginning to contain your demonstration data, and then do everything exactly the same as we discussed before. And that will, in some cases, work decently well. So this is an example from a paper that uses actually DDPG, which you can think of it as roughly a continuous version of Q-learning, to drop a bunch of demonstrations into a replay buffer and learn a variety of like robotic kind of insertion assembly type tasks. So this idea can actually work, but it does have a few problems. So both the importance sampling and the Q-learning approach have their downsides. With importance sampling, one of the major downsides is that you do tend to get stuck a lot. So using importance sampling with demonstrations does a good job of imitating the demonstrations, but often a bad job of doing RL. And here's why. If you look at the form of the importance weights, you can see that it's a product over a large number of time steps. And in practice, what that tends to do is it tends to create a loss landscape with a lot of long, flat plateaus. Intuitively, these plateaus are basically regions that are closer to one sample than they are to another sample. So if you have a really good sample here and a really bad sample here, so here's maybe a good sample, here's a bad sample, in between those samples, the objective value is essentially interpolating between them using these importance weights. But if let's say you have a Gaussian policy, those importance weights are actually pretty peaked, which means that in effect, the objective value between the samples almost looks like a nearest neighbor function. In fact, the higher dimensional your problem is, and the longer the horizon is, the more this thing starts to look like a nearest neighbor function. Which is maybe bad news, because if it looks like nearest neighbor, then policy gradient will in effect just pick the nearest and best demonstration and just try to match that without bothering to do any actual RL. And of course, this issue is exacerbated as you have longer and longer horizons. So what this plot is showing is basically the same thing as over here, but now with the additional time axis. And you can see that for low values of the horizon, here close to 0, the landscape looks pretty smooth. For high values here, close to 20, it looks very, very sharp. It's getting similar, more and more similar to nearest neighbor. For Q-learning, you have a different problem. For Q-learning, it has no trouble staying away from your demonstrations. Its problem is actually that good data is just not enough to do effective Q-learning. So to illustrate this, I'm going to use a little picture. Let's say the x-axis is the action and the y-axis is the Q value. And maybe the true Q function looks like this. So clearly the good action is right there, right? But if all you observe is the good action, in effect you're fitting a curve to this one data point, and lots of different curves might be equally good. So this curve is no worse than the blue curve if all you see is that data point. And in fact, this curve is no worse either. So if you only have good data, Q-learning can't actually effectively learn the right Q function because it needs to learn the shape of the Q function, not just the single good value. So it can match your single good value while producing a Q function like this curved green line that is wildly off in terms of what policy it results in. There are actually more problems with Q-learning that we can make a little bit more precise that are quite problematic in this kind of very off-policy regime where you include demonstrations that are very different from your greedy policy. So the trouble with highly off-policy Q-learning is the max. Remember that your Q function is trained on tuples s comma a drawn from your buffer. So we'll use this beta to denote the distribution over the buffer. So beta s comma a is the probability of seeing s comma a in your buffer. So what action will be selected when you do the max over the target value? Well, if you have, let's say, these 3 data points in your buffer, and again, this is the x-axis is the action, the y-axis is the Q value, you might hope that you'll fit a Q function like this, and then when you do the max, it'll select, obviously, the good one, right? The trouble is that if there are actions that you haven't seen in your buffer, your Q function might do this. It might decide that far away from your data, it'll get creative and make up some really arbitrary stuff. And in practice, neural nets do tend to be very creative. So if your Q function decides to do this kind of thing, then when you do this max, it might not pick this point. It might pick this point way out here. Now, the Q function in reality has no idea what's going on out there on the tails. But because it can extrapolate in arbitrary ways, when you do the max, in effect, you're kind of asking the Q function, what is the action for which you made the biggest mistake in the positive direction? So it's kind of the recipe for producing garbage out of your Q function if you have out-of-distribution actions. Now, it turns out that regular Q-learning algorithms like the ones we discussed in class tend to avoid this issue because they use some noisy variant of the latest Q function to collect their data. So when you collect new data by using your Q function, you're going to be sampling actions that are close to the max. So if your Q function erroneously thinks that this thing is really good, it'll probably go and do it in the real world, collect those transitions and add them to your buffer so that when you train on it, you won't have any problems. But if you use highly off-policy data like those demonstrations, then you might not actually visit the same states as the demonstrations, especially early on during training, and you might get these spurious peaks, train on them, and get a bunch of garbage. So this can be a big problem with off-policy Q-learning. Far off-policy Q-learning. Is a question?
This is similar to like the issue of why we have like a target network, right? Like we choose the max according to one policy and then calculate the Q value according to another policy. So why isn't this solved under?
Yeah, so the question was, well, isn't this kind of why we have target networks or that like double Q-learning thing and so on? Certainly, techniques that mitigate overestimation, like target networks and double Q-learning, do mitigate this problem. However, remember that the target network is still just a lagged version of your current Q function. So you won't be able to eliminate all mistakes, and you won't even be able to eliminate all correlations between mistakes. Now, one might argue that if you have like a large enough ensemble of Q functions, maybe you will eliminate them. In practice, that doesn't really seem to be the case. Okay, so basically the problem happens if the argmax of your Q function has a small probability under your buffer. So if you choose the action according to the argmax, and that action is extremely unlikely under your buffer, meaning it's an out-of-distribution action, then it might be one of these spurious peaks that is not actually good, but that your Q function thinks is erroneously good simply because it made a mistake there. Now, of course, then that value ends up getting propagated via the Bellman backup, so you end up training on this garbage value, and it gets pushed further and further back through the MDP, which means that even in-distribution actions will then end up having garbage values because they have garbage targets. So it sort of spreads through your Q function once you start making those mistakes. If we want to think about mitigating this problem, let's first rewrite Q-learning in a slightly different way. It's actually exactly equivalent, but it just generalizes it a little bit. So let's say that instead of writing the target value as max Q, we'll just write it as the expectation under some policy pi nu. And if pi nu is just the greedy policy, then that's exactly the same as regular Q-learning. But you can make other choices. You can make it something other than the greedy policy. So then the question is, how do you pick pi nu? And the game that we're going to play is we're going to try to pick pi nu so that it's good, so that it has high Q values, while at the same time avoiding these nasty spurious peaks. And there are a few ways that you could think about doing that. So one choice is to keep pi nu close to beta. So you can estimate your buffer distribution and say, well, let's just make sure that the divergence between pi nu and beta of A given S is small. So you could, for example, behavior clone your buffer and then just literally impose that as a constraint. So you could say the KL divergence between pi nu and beta is less than or equal to epsilon. And that will actually avoid visiting these spurious peaks, but in practice it can end up being a little bit too conservative because beta might be a very, very bad policy. So it might be that even though there's good stuff in your buffer, if you average over all the things in your buffer, on average they're not very good. So while this avoids the out of distribution actions problem, it might just result in a policy that's way too conservative. So, and of course you also don't know beta in general, so you have to estimate this thing using something like behavior clone. This is a little comparison of different methods for solving this problem. This is a fully off-policy training run. The green line shows naive reinforcement learning. This is kind of the distribution matching approach, which is this thing. Another thing you could do, which is a little bit better, and that's the orange line here, is to use a slightly more clever constraint, which is not just constraining the KL divergence, but to constrain the support. To say, well, maybe we want pi nu that can be pretty different from beta, but it shouldn't be outside the support of beta. So if you can somehow estimate this region that contains these data points and just stay within that region, then maybe you don't have to be so conservative, but you can still avoid those spurious peaks. And there are a few different ways of doing this. This is still an active area of research. So one way of doing this that works decently well is to use something called maximum mean discrepancy to constrain the policy to the data. I won't talk about this too much, but if you want to learn more about this, check out these two papers that are at the bottom of the slide, and they'll talk in a lot more detail about the trade-offs of different kinds of constraints. Okay, so far we talked about pure imitation learning, which is easy and stable, but it suffers from distributional shift, and it can't get any better than the demonstrations. We talked about pure reinforcement learning, which is unbiased and can get arbitrarily good, but has the challenge of exploration and challenging optimization issues. We talked about initializing and fine-tuning, which is almost the best of both worlds, but could also sometimes be the worst of both worlds, because you might get distribution shift and not be any better off than doing RL from scratch. And then we talked about pure reinforcement learning, but with the demonstrations as off-policy data, which is still unbiased reinforcement learning, but the demonstrations don't always help, and it introduces some additional optimization challenges. So can we strike more of a compromise? Can we do like a little bit of supervised learning and a little bit of RL and do them together all at once? So there are, in fact, a class of methods that do exactly that. They actually directly combine supervised learning and reinforcement learning objectives, essentially using imitation as a kind of auxiliary loss function. So a very standard imitation learning objective is to maximize the log probabilities of your demonstrated actions given your demonstrated states, or some variant thereof. The RL objective is the expectation of the reward, or some variant thereof. So you could construct a hybrid objective where you literally just staple these two things together. You take the expected reward and you add the log likelihood of the demos times some coefficient lambda. And this might seem a little bit ad hoc, but in fact in practice it can actually work pretty well. You just have to be a little careful in choosing this weight here. So here's an example of a method that uses policy gradient to do this. So here there's a standard policy gradient term and a standard maximum likelihood term for the demonstrations. And when I showed those videos of the robotic hand manipulating objects, this was actually the method that was used to produce those videos. So there were some demonstrations collected via a glove interface by a person, and then those demonstrations were included in combination with reinforcement learning just by stapling the two objectives together. So that's nice because now you don't forget the demonstrations, unlike the pre-training approach. So they stick around forever, but you also don't have to do all this complicated, important sampling stuff. You can also do the same thing with Q-learning. So this is an equation from a paper by Hester et al. Called Learning from Demonstrations with Deep Q Networks or something like that. I don't remember exactly the name. But their objective for the Q function has 4 terms in it. So this term, which is kind of the interesting term, is essentially a kind of behavioral cloning term, except that because they're training a Q function, you don't just maximize the likelihood of the demonstrations because you have Qs, not Pi's. So what they do is they maximize the margin. They basically say the demonstrated action should be larger than all other actions by the largest possible margin. And then they have regular Q-learning loss. And then for some reason that is beyond me, they also have like a n-step Q-learning loss. And they also have some regularization loss because why not? So you just take a bunch of losses. But the important bit is this bit and the Q-learning loss. So, and they show that actually this works very well, that including the demonstrations and including this margin loss, which is the blue line here, actually substantially improves performance on a variety of Atari games, as opposed to naively including the demonstrations in the buffer without changing the objective. Okay, so what's the problem with these methods? Well, when you have a hybrid objective like this, you do need to choose that weight carefully. And the design of this objective, especially for imitation, takes a lot of care. So as you saw in the Q-learning slide, you have to use this kind of margin-based thing, which is not necessarily the most obvious thing. The other thing is that the algorithm becomes somewhat problem-dependent. If you're in a regime where your demonstrations are actually very good demonstrations, this might be a very reasonable thing to do. If your demonstrations are a bit suboptimal, then you have to tune that parameter carefully to trade off the suboptimality, and it never really becomes fully unbiased. So in practice, this sort of thing tends to work very well because it's simple, but again, it might end up being kind of the worst of both worlds if lambda is chosen improperly and the demonstrations are not very good. Okay, so to summarize, pure imitation learning, so easy and stable, but has distributional shift. Pure RL, unbiased learning, but has challenging exploration and optimization. Initialize and fine-tune, almost the best of both worlds, but can forget the demos. Pure reinforcement learning with off-policy data. In some ways, it's kind of the most unbiased, the most principled thing you could do, but in practice presents some optimization challenges. And this hybrid objective is a bit like initialization and fine-tuning, very simple, almost the best of both worlds, but it's no longer pure RL and maybe more biased. Okay, so that's it for today. On Monday, we'll have a guest lecture by Kate Rakelli on meta-learning, so I'll see you all then.